today's lecture we discuss about Fourier transform, and we all know that Fourier transform is applied for the non-periodic signals. Okay, Fourier transform is applied for the periodic or non-periodic signals. Okay, so here we discuss about continuous time Fourier transform CTFT, which is applied for a continuous time signals. So in this lecture we concentrate only on continuous time Fourier transform. If x of t is an aperiodic signal, we have to find out the frequency content of that signal x of t. As you all know that in the Fourier analysis, while discussing about the Fourier series, so we discussed about Dirichlet conditions. The same for the Fourier transform also, this condition should be satisfied. So firstly, the condition x of t mod x of t integral over minus infinity to infinity dt should be less than infinity. Okay, if this is satisfied, the Fourier series and the Fourier transform will exist. If this doesn't satisfy the Fourier transform, we cannot find out for the signal which is an aperiodic. Right. So let us start with the expression of the Fourier transform for a signal x of t, and we discuss about a Fourier transform pair here. X of t is the signal and x of omega is the Fourier transform, and this is the Fourier transform pair. Okay, x of t and x of omega. So for the signal x of t, the Fourier transform is given with the expression integral minus infinity to infinity x of t e power minus j omega t dt. Okay, and the inverse Fourier transform, I mean from the x of omega you can find out the x of t as 1 by 2 pi multiplied with the integral minus infinity to infinity x of omega and e power j omega t d omega. Okay, and these are the important expressions to find out the Fourier transform and the inverse Fourier transform. Okay. Let us start with the basic problems. So in any transform we start with the Fourier transform of delta t. Okay, so what is Fourier transform of delta t? Okay, so we solve this transform by using the expression x of omega, which is integral delta t. I am applying in the expression x of omega, which is in the range of minus infinity to infinity integral delta t e power minus j omega t dt. Okay, so you all know that this impulse is existing only at t equal to 0. Okay, with a strength 1. So even though we consider the integration from minus infinity to infinity, delta is existing only at t equal to 0. So at t equal to 0 the value is 1. So this expression will become as 1 multiplied with e power minus j omega t at t equal to 0. Okay, at t equal to 0, and this gives the answer as 1. So delta t Fourier transform is 1. Okay, and this indicates in the frequency domain, if you, this is the exact, I mean the horizontal axis is the omega, the frequency content, and the Fourier transform of delta t is 1. This indicates like this. This means it covers every frequency content. Okay, for all omega values, the frequency content is 1. So impulse function content, I mean impulse function Fourier transform is 1. This indicates it consists each and every frequency component with a strength 1. Okay, and here you have to be careful with the Fourier transform of delta t representation, that is the Fourier transform of delta t is not delta of omega. Okay, be careful with this such type of expressions. Don't represent the Fourier transform of delta t is not del of omega. Del of omega is simply like your delta function this one. Okay, for the horizontal axis in the omega, the independent variable is omega, and there the value is 1 at omega equal to 0. Okay, delta indicates whatever the independent variable, for that independent variable at 0 the value is 1. That is the impulse function. It may be a time, it may be a frequency, or it may be any other independent variable. Okay, so let us see another expression, x of t equal to e power minus at u of t. So what we learn now, the standard Fourier transform pairs, all are very important. Why? Because for solving of some problems we use all these Fourier transform pairs. Okay, so let us see such things. And here the condition is that a must be greater than 0, then only the signal will converge. Okay, otherwise the signal will not converge. You can find out the Fourier transform. So e power minus at u of t, the signal is represented as like this, e power minus at u of t. The signal is converging. Okay, it's going to 0 at some time. So we find out the frequency content for this one. So let us go for the expression once again, and we substitute that one. So integral minus infinity to infinity x of t e power minus j omega t dt. So you know that the signal is existing from 0 to infinity because of u of t. We change the integral from 0 to infinity, and x of t is e power minus at, and no need of representing u of t, and e power minus j omega t, and this will be dt. This will be integral 0 to infinity e power minus a plus j omega t. So this gives the expression as e power minus a plus j omega into t, a plus j omega. Okay. And this gives the answer as 1 by a plus j omega. So the Fourier transform of e power minus at u of t is 1 by a plus j omega. Let us represent all these standard transform pairs specifically. So we use these things. So this one is e power minus at u of t. So if you go for another one, a two-sided function, that is e power minus mod t. So let us take a also here. X of t equal to e power minus 8 mod t, modulus t. Okay. So for the t positive and t negative, the signal will exist. Right. So the signal, let us write this signal for t negative. Okay, for t negative, the signal is e power at, exponentially increasing from minus infinity to up to 0, like this. And for the t positive, the signal is e power minus at, it's exponentially decaying for the positive time. So this is the combination, x of t is the combination of these two signals. Okay, these two signals are converging. Entirely the x of t is converging from minus infinity to infinity. So you can easily find out the Fourier transform. So x of omega, I'm guidely representing. For the integration of minus infinity to 0, the signal is e power at e power minus j omega t dt, plus for the positive time, for 0 to infinity, the signal is e power minus at e power minus j omega t dt. So like solving the above one, okay, the previous problem, like e power a minus j omega into t dt minus infinity to 0 plus 0 to infinity e power minus a plus j omega t dt. Okay, so by considering the integrals in the range of minus infinity to 0 and 0 to infinity, we will get an answer 2a by a square plus omega square. Okay, and this is the Fourier transform of e power minus a mod t. So e power minus a mod t, the Fourier transform is 2a by a square plus omega square. And this is the third standard pair. Now we discuss some more things with the help of the properties. Okay, so before that, let us see the Fourier transform of a constant value which is 1. So what is Fourier transform of 1? So how to find out the Fourier transform of 1? So we don't directly go for the traditional approach to calculate the Fourier transform of 1. So we take here an impulse function in the frequency domain. So let delta omega, which is represented like this, already discussed in the previous problem. Delta omega is, the value will be 1 at omega equal to 0. So we go for, we are going indirectly to find out the Fourier transform of 1. Okay, so the frequency domain, the del omega is 1. So we find out the inverse Fourier transform of del of omega, that is f inverse of del of omega. We are going to calculate f inverse of del of omega. Okay, so f inverse of del of omega is 1 by 2 pi minus infinity to infinity del of omega e power j omega t dt. Okay, so what this the expression will be 2 pi. You know that del omega is 1 at omega equal to 0. Okay, so 1 e power j omega t at, not t, at omega equal to 0. So this will be 1 by 2 pi. So the inverse Fourier transform of del of omega is 1 by 2 pi. Okay, so I will bring this 2 pi to the left hand side. F inverse of 2 pi del omega is 1. So this is, the 1 is the inverse Fourier transform of 2 pi del omega. So 1 is inverse Fourier transform of del omega. That indicates the the Fourier transform of 1 is 2 pi del omega. So got the result, that is the Fourier transform of 1 is 2 pi del omega. So this is nothing but in the frequency domain omega, at omega equal to 0, there is an impulse with strength 2 pi. Okay, this is time domain, that is 1. This is time domain signal. Okay, in the frequency domain we got an impulse. So we again mark this expression. So now let us see the properties of the Fourier transform. Why I am directly going for the properties means, by using the properties of the Fourier transform we can solve a lot of problems. Okay, so starting from the linearity, we discuss around 10 properties, and with using the help of such properties, let us go for the solving the problems. So let me go for the properties. Properties of the Fourier transform. Properties of Fourier transform. So the first one is linearity. So what are the properties we discussed in the Fourier series or Laplace transform, jet transform? The same properties again we discuss here. The first one, linearity. So for the signal x1 of t, the Fourier transform is x1 of omega, and for x2 of t, the Fourier transform is x2 of omega. So for the linearity, to do the linearity, a x1 of t plus b x2 of t, the Fourier transform is the linear and weighted combinations of x1 and x2. A x1 of omega plus b x2 of omega. Okay. And second property, time reversal. X of t Fourier transform is x of omega, and x of minus t Fourier transform is x of minus omega. Okay. Third one, time shifting. These are the important properties: time reversal, time shifting, frequency shifting, time shifting. X of t Fourier transform, while representing any property, initially have to represent like this with pair. We are taking x of t and we are shifting that x of t, x of omega. If we shift the signal like this, t minus t naught, okay, the signal is x of t minus t naught, the Fourier transform of such signal will be x of omega into e power minus j omega t naught. Okay, you know x of omega, and that x of omega is multiplied with e power minus j omega t naught, and x of t plus t naught, with x of t plus t naught, x of omega and e power j omega t naught. Okay. And here a delaying any signal by t naught doesn't change its the magnitude spectrum. Okay, and where the phase spectrum is changed by the by such value like minus omega t naught and minus omega t naught or omega t naught. Okay, so time shifting of your original signal doesn't change this magnitude spectrum, but the phase will be changed. Okay, and that change is represented by these terms, minus omega t naught and plus omega t naught. Okay, and the fourth one, frequency shifting. So in the frequency shifting, x of t Fourier transform is x of omega, and we go for the frequency shifting, that is omega minus omega naught, some shift by omega naught. and its x of t will be x of t e power j omega naught t. That x of t is multiplied with j omega naught t. Okay. If x of t is multiplied with e power j omega naught t, you will observe the shift in the frequency domain. Okay. So if x of t is multiplied with e power minus j omega naught t, this will be x of omega plus omega naught. And you can remember this representation. If you observe here, in time shifting minus t naught, and in the frequency you will get the minus t naught, minus j omega t naught. If it is plus t naught, in the frequency you will get plus j omega t naught. But here it is reverse, plus j omega t naught, and you will get minus omega naught, the shift in frequency. Here minus j omega t naught, and you will get the plus. Okay, this is quite reverse in time shifting and frequency shifting. Okay. So here I will discuss an example, the frequency shifting, similar to the modulation property. You can say this one, that is x of t multiplied with cos omega naught t. Okay. So I write this expression as 1 by 2 into x of t e power j omega naught t plus x of t e power minus j omega naught t. So this entire expression I can write it as the Fourier transform of x of t, left hand side and right hand side, cos omega naught t. The Fourier transform applied for the left hand and right hand side, sorry, I mean x of t and cos omega naught t, we can go for that x of omega minus omega naught plus x of omega plus omega naught. Okay, we will discuss this thing in the modulation property. Okay. So x of t is signal. If you multiply with if you multiply with the cos omega naught t, the x of t spectrum will be shifted to omega naught and minus omega naught. Okay, so that is, let us consider the x of t, the signal is like this. The signal is like this. If its spectrum is represented like this, that is x of t and x of omega. If this x of t is multiplied, okay, if x of t is multiplied with cos omega naught t, cos omega naught t, its Fourier transform will be, the spectrum will be shifted to two positions, minus omega naught and plus omega naught. Okay, if this is a, and this will be a by 2. Okay, so we will discuss how this will be shifting to two different frequencies, minus omega naught and omega naught, while discussing about the frequency domain of cos omega naught t, or a Fourier transform of cos omega naught. Just keep in observation. So next property, time scaling. Up to the fifth one, time scaling. Time scaling property. This time scaling property, x of t, the Fourier transform is x of omega, x of at, the Fourier transform will be 1 by mod a x of omega by a, that is provided that a greater than 0. Okay, if a is less than 0, you will have the negative value, okay, minus 1 by mod a. Right. So this is the time compression of signal related to the spectral expansion or time expansion of the signal, which is related to the spectral compression. Okay, time compression, spectral expansion, time expansion and spectral compression. So you can like relate the time compression, the spectral expansion. The time expansion, spectral compression. Okay, and this is time domain and this is the frequency domain. Okay, in time domain the signal is compressed, in frequency domain the spectrum will be expanded. Okay, in time domain the signal is expanded, its frequency representation will be compressed. Okay. Next, conjugation property. X conjugate t, the Fourier transform will be x conjugate of minus j omega. Okay, the conjugation of x of t, the Fourier transform will be x conjugate minus omega, not minus omega or minus j omega. Let me represent with just omega. Next, the seventh property, convolution. An important property, x1 of t Fourier transform is x1 of omega, x2 of t Fourier transform is x2 of omega. If you go for the convolution of x1 and x2, x1 of t convolution x2 of t, in frequency domain this is the multiplication of individual Fourier transforms, x1 of omega multiplied with x2 of omega. So in time domain, if you go for the convolution, in frequency domain it is multiplication. Okay, and if you go for the multiplication convolution, okay, I'm sorry, multiplication frequency, multiplication in time, okay, we go for the convolution in frequency, that is x1 of t multiplied with x2 of t. This Fourier representation is 1 by 2 pi x1 of omega convoluted with x2 of omega. Okay, these are also very important properties. Easily you can solve the convolution of any signals in time domain if you know the frequency domain representations. Next, time differentiation. Time differentiation, x of t Fourier transform, x of omega, if you differentiate x of t n times, and its Fourier representation will be j omega power n x of omega. Okay, j omega power n x of omega. If you for example, if you take the one time derivative, that is dx of t by dt, its Fourier representation is j omega x of omega. Okay, if you take the two time derivative, it will be j square, that is d square x of t by dt square, j square. Okay, j square, j omega whole square, that is minus omega square x of omega. Okay, ninth one, time integration. So integral minus infinity to t up to certain time, x of t dt, its Fourier transform will be x of omega by j omega plus pi del omega into x of 0. Okay, x of 0. X of omega is the Fourier transform of x of t. X of 0 is the value at omega equal to 0. Okay. Last, duality property. Important one. X of t Fourier transform is x of omega. If capital X of t is the signal represented capital X of t, the Fourier transform you can get 2 pi x of minus omega. Okay. We know that x of t Fourier transform is x of omega. We got some signal. If this x of omega, if it is signal is in time domain, capital X of t, we can find out the Fourier transform of this capital X of t with the help of x of t, that is in place of t we can simply substitute with minus omega, that is with the help of 2 pi. Okay, 2 pi x of minus omega. Okay. Last one, Parseval's relation, Parseval's identity. Parseval's relation. It is integral x of t whole square dt. It is energy of a signal x of omega square d omega. Okay, so by knowing the frequency content you can find out the energy of a signal x of t using this Parseval's identity. Okay. Now using these properties with the help of some standard pairs, let us see the Fourier transforms of some different signals. Okay. Let us start with the Fourier transform of some exponential signal e power j omega naught t. So Fourier transform of e power j omega naught t. Okay. So for this one we use the Fourier transform of 1. So one Fourier transform is two pi del of omega. We have solved this one. If 1 is multiplied with e power j omega naught t, 1 is multiplied with e power j omega naught t. So what is the Fourier transform? So you can remember the frequency shifting property, that is x of t e power j omega naught t, that is x of omega minus omega naught t. Okay, so by using not omega naught into t, so by using this property we can solve this one. So in place of 1 in place of x of t we have 1. Okay, so x of t Fourier transform is x of omega. You know the Fourier transform of 1, that is 2 pi del omega. So we simply go for x of omega minus omega naught. We should not represent here t, x of omega minus omega naught. So e power j omega naught t Fourier transform is 2 pi del of omega minus omega naught. Okay. And similarly for e power minus j omega naught t, the transform is 2 pi del of omega plus omega naught. Okay, and these are some standard things. So by using the help of the frequency shifting property, we can solve this type of examples. Okay. Now let us go for another expression, problem solving, that is the Fourier transform of u of t. So how to solve the Fourier transform of u of t? Okay. So before solving the Fourier transform of u of t, let us solve the Fourier transform of signum function. Okay, why? Because we can represent this Fourier this u of t with the help of signum function. That is, u of t can be represent signum function as 1 by 2 1 plus signum function of t. Okay. That is, twice u of t is 1 plus signum of t. You know the signum function, that is, signum function is like this, Sgn of t, 1 and minus 1. Okay, if you add 1 to the signum function and if you make it half, you will get u of t. Okay, so to find out the Fourier transform u of t, you can take the help of the Fourier transform of signum function. Okay, so let us see the Fourier transform of signum function. Fourier transform of Sgn of t. So I use here another property, a differentiation property. Sgn of t, the signal is like this, minus 1, 1, and t. So I will compute the one-time derivative of the signum function. So I take the derivative of the signum function. So d by dt of Sgn of t, d by dt of Sgn of t. So derivative means you are going to find out the change in the signal Sgn. Okay, the derivative is finding the change in the signal. So you can observe from minus infinity to 0, the change is 0, that is, it is constant with a value minus 1. It is constant with a value minus 1. There is change, no change of value. So no change means 0 change. Okay, so the change is 0. Okay, the derivative is 0 up to 0. Okay, but at t equal to 0, the value is changed from minus 1 to 1. So okay, there is a change of value of strength 2. Okay, minus 1 to 1. So the change is represented by 2. And for the positive time, 0 to infinity, again the change is 0. Okay, so you represent the derivative of signum function with an impulse function at t equal to 0. Okay. So d by dt of Sgn of t is 2 del of t. Okay, 2 del of t. Okay, I am representing the derivative of signum function with help of a simple impulse. Okay, now I am applying the Fourier transform to the both sides, applying Fourier transform. So the Fourier transform of Sgn of t, let us take Sgn as x of t. You know the property, d by dt of x of t, the Fourier transform is j omega x of omega. Okay, so with the help of this one, d by dt of Sgn of t, that is j omega multiplied with the Fourier transform of Sgn of t. equal to the Fourier transform of delta t is 1. So 2 into 1. So the Fourier transform of SGN of t is 2 by j omega. So we got the answer. Fourier transform of signum function is 2 by j omega. So SGN of t Fourier transform is 2 by j omega. So we use this Fourier transform to compute the Fourier transform of u of t. So let us now see how to compute the Fourier transform u of t. The Fourier transform of u of t. So I represent the u of t with the help of signum function as 1 by 2 1 plus signum of t. So applying the Fourier transform to the both sides, the Fourier transform of u of t. Okay, I am keeping 1 by 2 outside. So the Fourier transform of 1 plus the Fourier transform of SGN of t. So what is the Fourier transform of 1? The Fourier transform of 1 is 2 pi del omega by 2 pi del omega plus the Fourier transform of SGN of t is 2 by j omega. So 2 will be cancelled out and you will get pi del omega plus 1 by j omega. So the Fourier transform of u of t is this one. U of t. So pi del omega plus 1 by j omega, and this is the Fourier transform of u of t, pi del omega plus 1 by j omega. Okay, so let us see another problem. Fourier transform of cos omega naught t. Cos omega naught t. How to solve it? So cos omega naught t can be represented as exponentials, right? Cos omega naught t is e power j omega naught t plus e power minus j omega naught t by 2. Okay. So I am applying the Fourier transform. I split down this entire expression as the Fourier transform of e power j omega naught t by 2 plus Fourier transform of e power minus j omega naught t by 2. Again we are going to remember the frequency shifting property. X of t e power j omega naught t. Fourier transform is x of omega minus omega naught. X of t e power minus j omega naught t. X of omega plus omega naught. So we use this property here. So the Fourier transform will be x of t is simply 1 here. This is 1. Okay. Already we have seen that e power j omega t 2 pi del of omega minus omega naught. Okay. So 1 by 2 pi del of omega minus omega naught plus 1 by 2 pi del of omega minus plus omega naught. We get pi del of omega minus omega naught plus pi del of omega plus omega naught. So this gives the Fourier transform of cos omega naught t. So this is nothing but in frequency domain, this gives the two impulses at omega naught and minus omega naught with strength pi. Okay, the Fourier transform of cos omega naught. So at the frequency omega naught, it will have the frequency components at omega naught and minus omega naught with strength pi. Okay. Similarly, you can solve the Fourier transform of sine omega naught t. Okay, and for this one, you can write it as, splitting this sine into exponential same as cos, the Fourier transform of e power j omega naught t by 2j minus e power, the Fourier transform of e power minus j omega naught t by 2j. Okay, and this will be 2 pi del of omega minus omega naught by 2j minus 2 pi del of omega plus omega naught by 2j. Okay. So 2 will be cancelled out, and if you change this denominator j into the numerator, you can make it as minus pi j del of omega minus omega naught plus pi j del of omega plus omega naught, the Fourier transform of sine omega naught t. And this spectrum is two impulses at the same frequencies, but the strengths will be different, positive impulse and negative impulse. Fourier transform of sine omega naught t. Okay, so like this, with the help of the properties, you can solve the Fourier transform problems. Okay. So in another lecture, we will discuss in detail more about some more problems where we can solve it with the time differentiation property, integration properties, convolution properties, all this. Thank you.